r square. It is also obvious that this force is not same for every medium. For example, if the bodies are kept in air, the force is different from the force while they are kept in water. Variation of force according to the medium is determined by a constant. Say this is K. Finally, we can say that force F equals Q1 into Q2 divided by K into R square. This is nothing but the expression of Coulomb's law. In SI system, force is measured in Newton, distance is measured in meter, charge is measured in Coulomb, and K equals 4 pi epsilon 0 epsilon r. The force acting between the charge is expressed as F equal to Q1 into Q2 divided by 4 pi epsilon 0 epsilon r into r square, where epsilon 0 is the permittivity of air or vacuum and its value is 8.854 into 10 to the power of minus 12 farads per meter, and epsilon r is the relative permittivity of the surrounding medium in respect to the permittivity of air or vacuum. So hope this discussion helped in better understanding of Coulomb's law.
So F equals to Q1 Q2 upon K r square. So the factors which affects the Coulomb's law are if the two charge carriers Q1 and Q2. So as we see that if you are making the constant Q1 and you are just changing the Q2, then the force are increase or decrease. Similarly, if you are unchanged the Q1 and you are just changing the Q2, then again the force appears is changed. So forces also depends upon the Q1 and Q2. Similarly, if you are just kept near to that Q1 and Q2, then again the force is affected, or if you are just making the distance between that Q1 and Q2, then again the forces are affected. So F is affected by Q1, Q2 and the distance between them. And you just put over there one constant that is known as the Boltzmann constant K, that depends that is the value that is 4 pi epsilon 0 epsilon r, where epsilon 0 is the permittivity of free space air and the epsilon r is the permittivity of relative permittivity with related to the whether the medium is the air, whether the medium is the water or any vacuum. So F is, again we can see observe whatever the force is applied between the Q1 and Q2, that is proven with the Coulomb's law. Now the next question. Question number 2a. Define the RMS value of alternating quantity, that is AC4, and derive the expression for RMS value in terms of maximum value for the sinusoidal alternating current. RMS value, which stands for the root mean square value, that is RMS, root mean square. So you have to just taking the under root of whatever the value you are just finding, that is the mean, that should be a mean value, and for that mean value you must take the root square, and so whatever the final result, that is known as your RMS value. Now as we just talk about the DC current, that is the fixed. At all the instant the level of your DC is the fixed, but AC current, it is varying from instant to instant. So there is a necessity to just determine the effective value of that AC, there is one standard platform should be defined. Just we go through one example. First time just talking about the DC. For that, so it has some level like +5, so it is the straight line, like it is a -5, then it is again straight line. So each and every instant T1, T2, T3 up to Tn, anyone, you just find out that each and every instant you get the fixed value. and again at any instant it has the some negative value. So in DC the value is unchanged, but that is not same for the AC. Like we just talk about the AC, the current starting for the 0 level, this one is the maximum magnitude. So current starting from the 0 reaches to the peak level, decrease, again reaches to 0, starting with the negative line, 0. So this is a continuous alternating waveform whereas the two positive half cycle, one positive half cycle, one is a negative half cycle. It has different instant like T1, T2 up to T3, somewhere T4, anyone. So you are just getting that at the T1 instant you have some different value. At the T2, again the T2 has the value which is different from the T1. Similarly at the T4, like it has a higher value. So in AC waveform what happens, each and every time of instant you are just getting the different values of that particular signal. So there should be one particular platform which gives the common value or the standard value of that signal, and that is given with, that standard is given with the RMS. So that common platform which we already talked that it is defined finding amount the heat produced by both the current AC and the DC. So whatever the heat is produced by the DC, that exactly same we get from the AC. So for by bridging that AC and DC, there should be some common platform, and that platform is provided by the RMS value. So now finally the definition of that RMS is, it is equal to the DC value which we when the flowing through the given circuit for a given time produce the same heat which is produced by the AC when the flowing through the same circuit current for that same time. So whatever the heat is produced by the DC, if it exactly equal to the heat produced by the AC, so that the common platform which makes that value equal, that is the RMS value. So you just make the equation that RMS current, that is RMS, equals to Im, that is the maximum current, divided by root 2. RMS is equals to Im by root 2, that is the equation for any AC current which has the same heat produced by the DC value, DC current. Now just go through the derivation of the RMS. The equation of the sinusoidal AC is given by I equals to Im sin theta. See here, that is our AC waveform which has the value that I, that is the instantaneous current, that has the value Im sin theta, because this is a sinusoidal waveform. So this is the equation, instantaneous equation. The square of that instantaneous value of the current is I square, and the mean of that square of the instantaneous value of the current over the half cycle is given by I square, because we have to we just have to get the square of that value. So and for the half period, then it is, again I am just defining that 0 to pi, that is a half cycle for positive, and this is negative half cycle for 2 pi. So this is half cycle, that is a 180 degree, and full cycle contains the 360 degree. So we are just talking about that portion, only the half portion. That's why here we just taking the integration of 0 to pi. So the area covered by that is the I square d theta upon 1 by pi, because we are not talking about the negative cycle. That's why our negative cycle is getting the 0, and whatever the current we just covered from the positive half cycle, that is pi. So you are just taking that I square equals to, now pi is the common, so just kept before that main equation, that is 1 by pi. equals to integration of 0 to pi, that is area covered by the cycle, into I square d theta. Now that one is a variation with the theta, that's why d theta is taken. Now I square equals to, next step, equals to 1 by pi integration of 0 to pi. Now put the value of I, that is Im sin theta raised to whole square into d theta. Now Im is again the constant value which is not depends upon the theta, that's why we just kept it outside the equation. So we are just getting that I square equal to Im square by pi integration of 0 to pi sin square theta d theta. The next one, I square equals to Im square by pi integration of 0 to pi. Now here what happens, you have to just put the value of sin square theta by using the mathematical equation, that is sin square theta equals to 1 minus cos 2 theta by 2. This is the mathematical derivation. So instead of writing the sin square theta, you are just putting the 1 minus cos 2 theta by 2. So now the next equation becomes that, yeah, again the 2 is a constant, so you just kept outside the equation. So you are just getting the next equation, that is I square equals to Im square upon 2 pi integration of 0 to pi 1 minus cos 2 theta d theta. Now taking the integration of 1 and cos 2 theta with respect to theta, we getting that I square equals to Im square upon 2 pi. Now the 1 is a constant, so with respect to d theta, its integration is theta minus cos 2 theta. Minus is same, cos 2 theta has the integration of sin 2 theta by 2. Integration of cos 2 theta is sin 2 theta, but integration of 2 theta is 1 by 2. So cos 2 theta is sin 2 theta by 2. Now limit is 0 to pi. So first putting the maximum value of the limit, that is pi, and then the lower limit, minimum limit or the lower limit, that is 0. So we get that I square equals to Im square upon 2 pi into bracket theta, instead of theta the first putting the pi, sin 2 pi by 2 minus 0 sin 2 into 0 by 2. We know that the value of sin 2 pi is 0 at the any instant of 0, pi, 2 pi, 3 pi, 4 pi, any n pi, the value of sine is 0. So we just neglect that value, and again the sine 2 into 0 is also 0. So sin 2 theta by 2 equation is neglected. So we are just getting that I square equals to Im square by 2 pi into pi. Now pi is cancelled out. So we get that I square equals to Im square by 2. Now if we are just removing the square of the left hand side, you are just getting that I equals to Im by root 2. So the IRMS value is written like that, the under root of mean of the square of the instantaneous value of the current. So IRMS equals to Im by root 2. Putting the value of 1 by root 2, we are just getting that IRMS equals to 0.707 into Im. So here you just find the value of IRMS. This is the 0. If this is current, this is some maximum value of the current. If this is your current, so here you are just getting any IRMS value which is IRMS. Many times you just find that it is the average value upon equal to Im by root 2, or we can prove that 0.707 into Im. So this is the value of IRMS. Now just go through one video which just something talk about the root mean square value.
You are all familiar with three concepts of average: the mean, the median, and the mode. These are a good start to averaging, but are not the end of the story. There are more types of average measure depending on the situation you find yourself in. Root mean square is another type of average that gives you an average value of the magnitudes of a variable. It is particularly important in the study of AC currents, as the mean would give us a value for current around 0, which suggests that negative current has no use. This isn't the case. Negative and positive currents are equally as useful, so we need to find a way to make those negative parts of our sine wave positive and then average across them. How do you make a negative positive, yet keep its identity? The answer is simple. You square it. 8 squared and minus 8 squared are the same. If we are only interested in the magnitude of a number, then squaring it allows us to have just that. Only positive values all the time. Doing this gives us lots of peaks on a graph that are far bigger than the peaks or troughs were before. How do we bring these peaks back down to size? The answer is simple. You square root it. But what if not all of these peaks are the same size? How do you account for peak variation? You account for it in the same way you would normally. You take a mean value. So, let's go through the steps. We want only positive values for our current, so we square everything. This makes it too big. We want to account for any variation in the magnitudes of these peaks, so we take an arithmetic mean. We want to bring these results back down to the size they were originally, so we square root them. This is how we do a root mean square. However, this can take a while to do for all the data you get, so it'd be nice to have a shortcut. If you know the value of a peak and you want to convert it to a root mean square value, then you can simply divide the peak value by the square root of 2 and you'll get the root mean square value.
The next question, that is question 2b, which also contains the 7 marks. One example. One coil, conducting coil, that is connected to a 200 voltage supply which has the frequency 25 Hz F. The coil carries the current that is 10 ampere whenever the supply is given to that coil.